Right, this video is going to discuss all about the centripetal or center-seeking force, which is the underlying thing of our circular motion stuff. So I've already said that tension can supply the centripetal force and acceleration in the last podcast. Now we're going to talk about how friction can. So anytime you're going around a curve in a car, you're actually experiencing a centripetal force. There's a force pulling you towards the center of that curve. That's applied by the friction between your tires and the road. So for drawing a free body diagram for this guy, here's our centripetal force going this way. Here's our weight of our car. Here's our normal force. So remember, centripetal force, it's always some other force. So in this case, it's the force of friction, because friction provides a centripetal acceleration in this case. So we got weight, we got normal force. If you remember, our frictional force equals mu times F sub n. So there's my free body diagram again. You either have big F sub little f, or since we're talking about static frictional force, I always like to do little f sub s for static frictional force. So oftentimes in these problems, we're going to ask you, like, what's the maximum speed that your car can have to go around a radius of a certain curve, or a curve of a certain radius, I should say. So we're going to make a little force chart. Here's everything in my x direction, y direction. So weight in the x direction is 0. It only goes in the up and down. So if we draw a little axis here, y, x. And weight in the y direction is going to equal negative mg, minus mg, because weight's going downwards. That's why we get that negative sign. Normal force, x direction, 0. Normal force, y direction, F sub n. Should we set up our Newton's second law problems, we're going to find out that this just equals mg. Our frictional force only in the x direction, and it's going to the left in this case, so that's why we have the negative mu sub s, whatever the coefficient of static friction is, times that normal force. And in the y direction, it's 0. So we add up all our forces in the x and the y direction. In the x, we know that because of Newton's second law, it equals mass times acceleration in the x direction, and in the y direction, it's going to be 0 because it's not going up or down. These forces balance each other out and they cancel each other out. So there's my lovely little chart again. So we're going to do the y direction first. You know, net force, mass times acceleration, but acceleration is 0 because the car's not going up in the air, thankfully. So that's all going to equal 0, and it's going to equal our weight plus our normal force. And we can solve that and see that our normal force equals mass times gravity, which we could already pretty much assume. Now in the x direction, our acceleration here is our centripetal acceleration. So we put a little c on that guy. So the net force in the x equals mass times acceleration equals just our frictional force, which is the negative of the coefficient of static friction, the maximum that we can have, times our mass times gravity, because that's our normal force, mg. And remember I said, things are going crazy today. Remember I said in a previous PowerPoint that this acceleration, the centripetal acceleration, equals v squared over r, so we can plug that guy in. Then we're just going to solve for v. So the fastest we can go is determined by this. It's the square root of whatever our coefficient of static friction is, times our gravity, times the radius of the car. So you see the mass of the car doesn't even matter, because the masses cancel each other out. So the velocity only has to deal with the coefficient of friction and the radius of the curve, because gravity is a constant. So a car travels at a constant speed around two curves. Where is the car most likely to skid and why? We just found that equation. So we can just use this guy. We can see that if this r is smaller, that means the f is going to be bigger. So that means it requires a larger force for a smaller curve. If this r gets bigger, our f gets smaller, because we have r on the bottom here. Every time we increase this, it's going to decrease our f. So the bigger the radius, the smaller the force. So it's easier to go around big curves than it is to go around small curves. It requires less force. So some stuff we already talked about, just to remind you, in case you're not watching all these videos end to end, because you know, there's nothing better to do on a weeknight. A little c means center seeking. It means our centripetal forces, our centripetal accelerations. They always point towards the center, whatever curve or circle we're talking about. Our velocity is tangent to the curve. It has a constant velocity. Its magnitude is constant, I should say, but its direction is not. Velocity is a vector quantity, so that means it has magnitude and direction. But if my magnitude is constant and my direction is not, that means I am accelerating because I'm changing my velocity. And this velocity is perpendicular to the centripetal force and the centripetal acceleration. Radius is the perpendicular distance from the axis to the object. We all know what radiuses are. And when we're drawing our free body diagrams, never write F sub c. Because F sub c can be either a frictional force, it could be a tension force, it could be a normal force, it can also be a gravitational force. Don't write F sub c. It's one of these other forces. Projectile motion is not true circular motion. Why? Well, because the acceleration in a projectile is always downwards because it's gravity. Now, if it was true circular motion, then our acceleration would always point towards the center of this curve. So it's not true circular motion. Also, it's because of what it says right there, that circular motion, the force is always perpendicular to the velocity, but in our projectile motion problems, like our velocity starts here, goes like that. But acceleration is always downwards. That guy's not perpendicular. The only place it's perpendicular is right at the very top. So just some practice drawing some free body diagrams. So here's an object tied to a post, moving in a circle at a constant speed on a frictionless horizontal surface, coming straight out of the paper. So it's coming right at you. So we're going to draw the free body diagram for here. We have its weight. We have its normal force since it's resting on a table. And we have the tension force. Remember, I don't draw centripetal force. I don't put a C here. There's a string. That means it's going to be a tension. And our acceleration is also towards the center. Don't draw your acceleration touching your object. Draw it off to the side like I just did. And then we're going to do our Newton's second laws. For some reason it cut off my Y here. So the net force in the x direction equals mass times our centripetal acceleration. Net force in the y direction equals ma, but that equals 0 because it's not going up or down. It's only coming straight out of the paper, so it's only moving in the x direction. So we add up all of our forces. So we know that our force is our tension force, and it equals mass times acceleration. And over here we know that our normal force equals our force of gravity, because that's how we get it whenever we do our Newton's second law. Now, this one got cut off a little bit too. Anytime you see this little f sub v, it just cut off my y here. So this time, this rock is tied to point A, which is hidden behind this out of a paper thing, out of the paper. It's moving in a horizontal circle at a constant speed, and it's not resting on a solid surface. There's no friction, and it's coming straight out of the paper. It's coming towards you. So in this case, our free body diagram is going to look like this. Still got our weight pulling straight down. We got our tension acting along the string. So our tension goes like that. And our acceleration is towards the center of the circle. Now in this case, we're going to have components for our tension. It's going to have a y component and an x component. And it's not going up or down, so we know the net force in the y is 0. And we're talking about the x component of this tension, so we're going to use the cosine to get that guy. Mass times acceleration. So the tension times the cosine of whatever angle this is in here equals our mass times centripetal acceleration. And similarly over here, we're talking about the sign because we're talking about the y component. And this tension's y component is going to equal the weight of the object. Hanging from a rope, and it's just hanging there. It's got the force of gravity going down, tension going up, no acceleration at all. So only thing we're going to get from this guy is our tension equals the gravity, which you could have figured that out even probably without physics. This time, this rock is riding on a horizontal disc that is rotating at a constant speed about this axis right here. And friction prevents this guy from sliding off the table. And the rock is coming right at you out of the paper again. So we got gravity going down, normal force going up because it's resting on the surface, and we got a frictional force pointing towards the center. It's also accelerating towards the center because, you know, our centripetal force and our acceleration point in the same direction. Now it's not moving up or down, so net force in the y is 0. And since our force is going to the left, negative frictional force equals mass times negative centripetal acceleration. So our centripetal force here, our frictional force equals our mass times acceleration. And again, we get our normal force equals our weight. This time we're spinning a rock inside of a cone. Gravity down, normal force at an angle because the surface is like this. Normal force acts parallel. And our acceleration is towards the center. So in this case, our centripetal force is supplied by our normal force. So our centripetal force is actually the x component of this normal force. And there's our little angle. We also have a frictional force keeping this guy on the side of the cup so he's not sliding down. Or, you know, if they spin it, he wants to go upwards. Our frictional force is pulling him back this way. So its x component's also going to supply some of the centripetal force. Now it's not going up or down, net force is y. In this case though, we're talking about this guy's x component, which is going to be the sine of this angle, and this guy's x component, which is the cosine of this angle, cosine of that angle, equaling our mass times acceleration. Get rid of all of our negatives, and we can see that the x component of the normal and the frictional force equals our ma. In this case, we're talking about our y's. So the frictional force is y, the normal force is y, and gravity is all y. And they all add up to 0. So, you know, solve for whatever we don't know. This one's kind of interesting because you've probably been on an amusement park ride kind of like this where, you know, you start spinning around in a circle and the floor drops out. And we got some frictional force keeping us on the side of the wall along with some, you know, centrifugal force, even though I don't like that word. But we don't put centrifugal force on here because it's not a real force. So we still got our gravity going down, we got our friction going up, and actually all of our centripetal force this time is supplied by the normal force. Since we're touching a surface, normal force acts towards the center. Acceleration's all center. Not moving up or down in the y. And you figure out our normal force is our only centripetal force working here. And we can also figure out that our frictional force equals our gravity. Now we're swinging on a rope. We got gravity going down, tension going up, acceleration going up. No x direction stuff here at all. Only worried about our tension and our gravity. So our tension, which is our centripetal force in this problem, equals our weight plus our ma. Same kind of concept, except this time it's at the very top. In this case, our gravity goes down and our tension force goes down. So our centripetal force goes down. Acceleration's all down. No x movement, so we get rid of all the x direction stuff. And we're just left with all this fun stuff. Too fast. So our tension force and our gravity force are supplying the centripetal force in this case. So problem number 1. If the radius of a circle is 1.5 meters and it takes 1.3 seconds for a mass to swing around it, which is 1 revolution, what is the speed of the mass? And we need to find the tension of the mass. tension of the situation if the mass is 2 grams. So we know that our velocity equals 2 pi r over big T, but what's our big T equal? And we're talking about seconds per revolution, so 1.3 seconds per 1 revolution. So plug everything in, we get 2 pi times 1.5 divided by 1.3 should give us our velocity, 7.25 meters per second. Just double check that with a calculator. Turn on calculator. 2, where's the pi button on this? Pi times 1.5 divided by 1.3. Oh, 7.25. And define the tension. So we need to find out what force we're talking about here. So we draw the free body diagram for this mass. We got force of gravity going down, and we got tension going this way. So we know the acceleration is also going this way. So we do our net force, X equals MAC equals FT. So all we got is Ft equals our MAC, but remember A is V squared over R. So M times our 7.25, our M is 2 kilograms. Gotta square that, divide by 1.5. Bring my calculator up. So 2 times 7.25 squared divided by 1.5, 70.81, actually 70.1 newtons. 70.1 newtons. Alright, another problem. 1,200 kilogram car traveling at 8 meters per second, turning the corner with a radius of 9 meters. How large a force is needed to keep the car on the road? So we're going to find out what force we're talking about here. So we draw a free body diagram first. We got force of gravity, normal force, and we got its frictional force going that way. So we're going to see if we do our net force. Oh, we got an acceleration. Net force in the x direction is going to be equal to mass times acceleration, centripetal, which just equals our frictional force. We know our frictional force is mu Fn, but for part A, we just need to worry about this part. So we're trying to worry about how big of a force this is. So mass, remember AC equals V squared over R. So 1,200 kgs times 8 meters per second squared divided by 9 meters. And you get a frictional force of 8,533 newtons. So to find our coefficient, we need to do FF equals our mu sub S times our normal force. If we do our y direction stuff, we'll find out that our normal force is just our weight. It's the only two forces acting in the x or the y direction. So our normal force is going to equal our mass times gravity. So we solve this guy for mu sub s, and mu sub s equals our frictional force divided by mg. So 33.3 divided by 1,200 times gravity. And you get our mu sub s of 0.726. Number 3, traveling on a circular flat track with a speed of 20 meters per second. Coefficient is that much. Calculate the radius needed to keep the car on the track. So to do this, we're going to do some basically the same thing. This time we've got force of gravity, normal, friction, acceleration, and we'll do the y direction stuff. It's not going up or down on the y, so we know that our normal force just equals mass times gravity. We do it in the x direction, and AC, and that just equals our frictional force, which equals that. So you get our frictional force equals mu sub mu sub s times mass times gravity. So now we have to think about what we got here. So if we know that combine all this stuff, so we know that mass times our centripetal acceleration, which is v squared over r, equals our frictional force, which is mu sub s mg. M's are gone. Trying to solve for r, because we're trying to find the radius needed here. So r is going to be equal to v squared over mu sub sg. Now we can just plug our stuff in. We got 20 squared divided by 0.25 times 9.8. So just a lot of algebra, and you get a radius of 163.27 meters. That's a pretty big curve, because that's a pretty low coefficient of friction. All right, if you ever watch a NASCAR race, or if you ever drive and get on the highway, you'll notice that sometimes curves are banked. And there's a reason for this, and it has to all do with physics, all do with centripetal forces. So when we bank the curves, we actually increase the centripetal force, which can make us go faster. We're allowed to go faster. I will show you why. So engineers have learned to bank curves so that cars can safely travel around the curve without relying on friction at all to supply the centripetal acceleration. So in this picture of this car going on this like a little bowl-shaped curve, how many forces are acting on this if we assume that there's no friction? So if you look, the only force that's acting on it is this normal force. And what's applying the centripetal force here is the x component of this normal force. So we don't need friction at all to bank our curves. So here's our little x component. It's going to equal our mass times gravity if we do our net force in the y direction. And then over here in the x direction, our centripetal force equals our x component, which we know equals our mv squared over r. So the only forces we got acting this guy are gravity and the normal force. So we do a little chart. Weight in the x direction is 0. We got a component of the normal force in the x direction. We know that all equals up to mass times acceleration. Do the same thing in the y direction, except for we just have our weight going down, our y component normal force going up. That's all going to add up to 0. So we do a lot of math. We're going to do our net force in the y direction first, which equals our weight plus our y component of our normal force, all adds up to 0. We solve for our normal force, which is going to be, we just rearrange this with some algebra. We get our normal force equals that. Now the x direction is just the x component of the normal force. And that equals our mass times the centripetal acceleration. We know centripetal acceleration equals all that guy. So if we plug this into here, we get this equation. Then we just do a little bit of mathing around. We sine over cosine, it's the tangent. Divide this side by mg, we get rid of our m. So this equation right here is our equation for our banked curves. So for banked curves. So the tangent of the angle that our curve is banked equals our v squared, or tangential velocity, divided by gravity times the radius. So we can determine how much we have to bank our curve by using this equation. Almost done. So we have that equation. Nothing to do with friction, nothing to do with mass. It's all about the angle of the curve that we're banking. And that's it.